Okay, this is data mining with Weka 3.3 using probabilities. Okay, one thing we refer to is Bayes' theorem, which looks like this a little bit. And recall that this is the probability of one thing given another. It's probability of H given X. That's the way this is read. And the main point in the Bayes' theorem is that we have H given X here. We have the direction reversed here. That is, we have X given H here. So sometimes that can be convenient or make the problem easier if you can reverse the order. So that's the way I think of the value or the usefulness of Bayes' theorem. So H given X can be solved by X given H, plus you have to do some extra stuff when you reverse the order. But you can reverse the order using Bayes' theorem. Now, Bayes' theorem is just a theorem in math, and it's been used for a long time in statistics, but in machine learning, it's also useful. But sometimes the language, the way we talk about it, is a little bit different. So in statistics, usually when we talk about a probability like this, A given B, he writes it as H given E. So the first part is often called the hypothesis, and the second part is called the evidence. So this would be A would be the hypothesis, and B would be called the evidence when we're using the language of statistics. Now, when we're talking about data science, usually we're not usually talking about hypotheses exactly, and evidence. Well, evidence, we do think of things in terms of evidence, but usually we're saying given some evidence, we want to predict the class. That is, we want to know the probability of a class given some evidence or given the input variable or input variables. So we're trying to predict the class given some input, or we could call it evidence. So instead of hypothesis, usually in data science, we use the word class, but we could call the class the hypothesis. So we're hypothesizing that it's a particular class. Okay, so he uses the language of statistics and says that Bayes' theorem deals with hypotheses, whereas we presented Bayes' theorem for probability of A given B, he presents it with probability of H given E, and he calls H a hypothesis. Bayes' theorem can apply to any two events, but in machine learning and data science, we're trying to build classifiers. For example, we talked about classifying what kind of chocolate someone likes, white, dark, or milk. And so we would say, well, H or A would be that they like white, that we're testing a hypothesis that the person likes white, or we can just say we're trying to predict that what's the probability that the person likes white. So of course in naive Bayes, we need to do it for each of the classes, and then we choose the class that has the highest probability. So we have some evidence, and we're trying to say, okay, what's the probability given this evidence? What's the probability that the person would like white chocolate, given the evidence that we have? Or given the evidence that we have, what's the probability that they'll like dark chocolate? And finally, also, what's the probability that they would like milk chocolate, given the evidence? And then if one of them turns out to be higher than the other two, then of course we would predict that that one is the kind of chocolate they like. So like I said, we're concerned with questions like the probability that they like milk chocolate given the evidence, or given X. X stands for the input variables, but could also be called the evidence. Now, going back to statistics, just to see an example of how this looks in statistics, here's an example. Suppose a company that sells tires claims that their tires last for 100,000 kilometers. So what they usually mean by that is not that it lasts exactly 100,000 kilometers, but that it lasts at least 100,000 kilometers. Okay, we want to test whether this is a fair claim, and so we take a sample of 500 tires and calculate the average lifetime of these tires. So we can't check for all possible tires that this company makes, so we're just going to take a sample, and that's going to be the evidence. Then we use these results either to disagree with the company's claim or agree with it. So of course, if our 500 tires only on average last only 50,000 miles, that's probably going to be good evidence that the company is not making an honest claim. Okay, on the other hand, if all of our 500 tires, the average lifetime of the tires is like 130,000 kilometers, then maybe we would say, yeah, the company is not making a false claim. Okay, in statistics, they call the claim that the tires last at least 100,000 kilometers a hypothesis. They call the results of the test the evidence. So we do the tests on the 500 tires, and we find out how long, what was the average lifetime of those 500 tires. That's called the evidence. We may want to calculate probability of the hypothesis given the evidence. And if this probability is very low, so if the probability that they last more than 100,000 is very low, then we may have reason to say the tire company's claim is false. So that's the language that's used in statistics for the same thing that we can use in data science. That is the probability of A given B. So it's just different kind of applications, slightly different applications, slightly different language. But the math is the same. So this is why he switches from this notation to this notation, because he's using the hypothesis and evidence language. Furthermore, we could certainly use this language of hypothesis and evidence in our machine learning data science scenarios. So when we're doing, given the inputs, we're trying to predict whether the class is milk, that is, whether the person should be classified as liking milk chocolate or predicted to be liking milk chocolate. We could call milk a hypothesis and X the evidence. Okay, so the question here is, after that rather long explanation, the question is the probability of milk what we call the prior probability or the posterior probability? In class, we talked about this, and it's also available in the slides. And the word posterior means after, I think, in Latin. So after means given some information now, after being given that information, what's the probability of milk? So this kind of statement or expression is a posterior probability, but just the probability of milk, not given something else, not after being given something else, just the probability of milk is called the prior probability. So probability of milk without any givens here is the prior probability. Okay, so what about this? We're talking about the weather.nominal data set. So we're trying to predict whether someone is going to play golf or not. This is yes, they would play golf. And we're asking what's the probability of yes. That is also, because there's no given here. So that's a prior. Okay, what is the probability of yes? Well, I don't remember what the probability of yes is, but the class is either yes or no, so we just have to count up how many yeses there are. I remember there are 14 elements in the entire data set, so if there were 5 cases where they played golf, that is 5 cases of yes, then it would be 5 out of 14. If there were 9 cases where they played golf, then it would be 9 out of 14. And the same thing for no. If there were 9 cases of no, then it would be 9 out of 14. So the baseline prediction would just be what we got for this and what we got for this. That's called the baseline prediction. That's because these questions don't depend on any input values. It's just the prior probabilities, we could say, or just the probability without knowing any other information, any input information. So the prior probability is basically the baseline probability, and we know that 0R gives us the baseline probability. So 0R is just working with the prior probabilities. How can we use the priors to calculate the baseline classifier? Well, we just said that basically it's the same thing. They're both part of the calculation of the prior. An example of evidence would be, so this has no evidence in it. We're not asking given some evidence. Here we're not asking given some evidence, but an example of evidence would be that windy equals true. So that would be evidence. So then we could say, for example, what's the probability of yes given windy equals true? What is the probability of yes given that windy equals true? So what is the probability of this? So you have to go and look at the table. Maybe we should do that. Or look at the data set. Maybe we should do that. Okay, so I have the data set here. I'm going to, it's a little bit easier to see it in Excel than here. And also I want to manipulate it a little bit. I'm going to save this. For some reason my computer doesn't let me save it in that folder. I'm going to save it here as a CSV file, and then I'm going to try and open that. So it looks like this, and then I'm going to highlight which ones have windy equals true, just to make it a little easier to see. So our question was, what is the probability of yes given that windy equals true? So windy equals true, there's 1, 2, 3, 4, 5, 6 cases. And within those 6 cases, there are 3 yeses. So given that windy is true means we're only looking at the green. And then what's the probability of getting yes? That's 3 out of the 6. So I guess the answer would be 1/2. So what is the probability that if windy equals true, that we get yes? I think it's 1/2. Okay, next question. What is the relationship between a branch of 1R and a question like this? So we just saw that if we don't have any evidence, that is, if we're just talking about the prior probabilities, then we're really talking about the 0R classifier or the baseline classifier. I hope I said 0R earlier in this video, not 1R. So if we're using 1R, remember that means we're limiting our tree to just one variable or just one top node. We don't branch down to lower nodes. So if we're talking about the variable windy as the top or the only node, then we'd have windy up here. And for windy, there are only 2 possible values, so there's only going to be 2 branches. So we can have windy equals true or windy equals false. So we saw that when windy was true, we saw that here, that when windy was true, we had 3 yeses and therefore also 3 no's. So we had 3 yeses and 3 no's. Okay, now our question says, what is this? It says, what is the relationship between a branch of 1R and a question like this? So, for example, this question, what's the relationship between this question and the branch? So the branch is the evidence in this question. The branch here is the evidence. So we could have had a question like probability of yes given windy equals false. That would be, the evidence would be windy equals false. That would have been this branch. So a branch is the evidence. And then basically the purity of the node. Now this node is not pure, right? It's actually as impure as we could get, half and half. Pure means we have like all yeses or all no's. And this is right in the middle, so that's the worst that we could get. We would prefer that this was like 6 yeses. Then we would be very happy when we said that given that windy equals true, we would predict yes, and in our data set, it would have been 100% correct. So that's what we would like. On the other hand, this is the opposite of what we would want. But anyway, in the 1R diagram, what comes out here is basically what we get when we ask this question. I mean, by that, we got 1/2 here, we got 3 and 3. If we had gotten 5 and 1, then this would be, for example, 5/6. So what's here is basically what's here. Okay, and going back to the original to the question, what is the branch? The branch, that is this, is the evidence. Okay, here, if next question is an example, I guess I should have said this is for J48 because we're dealing with two variables. So we have more than just one node. So if we had evidence of windy equals true and humidity equals high, sorry, this is a true-false question. So an example of evidence, so is this true or false? An example of evidence could be windy equals true and humidity equals high. That is true. Going back to this one, what is this? An example of evidence would be windy equals true. That's also true. But this is an example of evidence for 1R, and this is an example of evidence for J48. Okay, sorry about that. Okay, what is the evidence and what is the hypothesis in this statement? So you look, everything to the right of the vertical bar is the evidence. So outlook equals sunny, and generally speaking, comma means and in probability. So here's a comma, that means and. Maybe. Okay, so here's a comma, here's a comma, here's a comma. So you would read those as and. So outlook equals sunny and humidity equals normal and windy equals true and temperature equals high. So all of that is the evidence, and the hypothesis is that they will play golf, or yes. Okay, so note that 1R never calculates a probability like the one in the previous question because 1R only deals with one variable. So we wouldn't be dealing with outlook and humidity and windy and temperature for the evidence. Of course, we always deal with the class. But when we say one variable, we mean one input variable. So when we're dealing with 1R, we only have one variable, like the probability of yes given outlook equals sunny. That would be a 1R calculation. Now, it could also be a J48 calculation if you had a very simple tree, or you might just need to know that. But 1R will never have more than one input variable. So suppose H is yes, the players will play golf, and E is windy equals high. Windy equals high, is that? Sounds like windy equals true, I guess is what I should have written there. So what is the probability of yes given H? I think that's the calculation we just did. Yeah, so I think we just did that. It's 1/2, I think. Okay, next question says, note that generally speaking, P of H given E is not the same as E given H. So you can't just switch these around. They're completely different questions. So they're not generally equal. So on the other hand, you can switch them and check to see what the answer is. So we actually did H given E. So we did this one. We could also, and we found that I think it was 1/2. And then here we could do E given H. So E means that it's windy. We could do that calculation. It's not really related to data science specifically, but we can do it. So we would do what? So we would identify the yeses. So we're saying given that it's yes, not given that it's true, given that windy is true, but given that play is yes, so we're reversing the order. So given that it's yes, so how many yes? So these are the yeses. There's 1, 2, 3, 4, 5, 6, 7, 8, 9 yeses. And within there, some of them are false, like this one and this one and this one. Some of them are true. This one is true, this one is true, and so on. So given that we're within the yes, what's the probability of getting true? So we just said there are 9 yeses, and within there, how many are true? 1, 2, 3. So 3 out of the 9, or 1/3. So the answer would be 1/3 to this question. So are they equal? No. Here we got 1/2. I believe I did the right calculation. And here we got 1/3, so they're not equal. Okay, so note that in the weather example, being able to switch from P of A given B to P of B given A, in other words, we talked at the very beginning about this theorem that's supposedly helpful in doing calculations. We said that the basic idea in terms of how it's helpful is that it allows us to switch the order here and here. So, is that of any value here? Like here, generally speaking, we're asking a question like, this one, for example. So the probability of yes given windy equals true. Well, we could use Bayes' theorem and ask like the reverse question, but it's really no easier. I didn't find it particularly any easier to do the reverse question than it was to do the original question. So in this case, doesn't seem to be very useful. That is, Bayes' theorem doesn't make our work any easier. It doesn't mean it's not true. It's true. I mean, we can switch and do a bunch of extra. We'll have to do some extra calculations. That is, we'll have to do this calculation and this calculation as well. But we could, and we would get the same answer that we got here. Actually, here we got 1/2, and here we got 1/3. But when we do all this extra stuff, we're going to end up with 1/2. So it does work, but it's not really any easier to do this calculation than it was to do this calculation. So Bayes' theorem doesn't really have any usefulness right now. So note in the weather example, being able to switch from A given B to B given A is not really of any benefit. One is no easier or harder than the other. Thus, you may rightly conclude here there is no reason to use Bayes' theorem here. But we are working towards developing the machine learning algorithm called naive Bayes algorithm, which is not the Bayes algorithm. But by the fact that it's not the Bayes theorem. This is not called Bayes algorithm. This is called Bayes theorem. Okay, but we're working towards naive Bayes algorithm. Of course, the name Bayes being in there, might lead us to think that it uses Bayes' theorem, and it does. But right now, in these calculations, it didn't seem to make any difference. Maybe it will as we proceed to develop this algorithm. Okay, so here I actually ask you to do this. That is, to show that this side is equal to this side for that particular calculation. So this would be yes given windy equals true. This would be windy equals true given yes. The probability of yes, you have to figure out that. And the probability of windy equals true, you have to figure out that. And this should hopefully give you the same thing as you got here. But the question is for you to do that. Okay, next is around minute 3, he begins to discuss the so-called naive assumption. So you have to watch the video, and he starts talking about something called the naive assumption. It is general, and the naive assumption is that events are independent. So you have to know what the word independent means, and we talked about that. It is generally not true that events are independent. For example, the event that you understand what was written in the previous question right here is not independent of the event that you understood what was written 5 questions before. So this is question 40. So like if you didn't understand what was written here, probably you're not going to understand what's written here. So the event that you understood what's written here is not independent of the event that you understood what's written here. So things are not generally independent. Events are generally not independent. Some events can be considered to be independent, but generally speaking, things are not independent. Thus, these two events are not independent. Generally speaking, most pairs of events are not strictly independent. Of course, there are events that are independent. For example, if you toss a coin 2 times in a row, getting head on the second toss is considered to be independent of getting a head on the first toss, right? We don't usually think that what happens on the first toss affects what happens on the second. So we call them, then we can call them independent. What you get on the second toss does not really depend on what you get on the first toss. Thus, we can say that the outcome of the second toss is independent of the outcome of the first toss. So those two events, what happens on the first versus what happens on the second, we can consider them independent. However, typically pairs of events are not truly independent. So like we said, we just saw an example where they weren't up here. However, the naive assumption in the naive Bayes algorithm is that events involved on the right-hand side of the naive Bayes theorem, so we have this stuff, that these are independent. Now, it's not quite like that, actually, but let's say it that way right now, that these are independent. Actually, the correct word is conditionally independent. But I don't want to go into that right now. We did that in class and in the slide. So the naive assumption in the naive Bayes algorithm is that the events involved in the right-hand side of the naive Bayes theorem are conditionally independent. This is therefore a naive or somewhat unrealistic assumption. That's what the word naive means. It just means like it's not really realistic. We're assuming that things are always independent, but we see that most of the time things are not independent. But this is the assumption made in our algorithm anyway. And in spite of the fact that it is unrealistic, it seems to work well. What does it mean to say that it works well? That is to say it does a good job of classifying. We're trying to build a classifier, and it turns out that after we go through this whole calculation and make our algorithm, it works well. In spite of the fact that we made this naive assumption, which isn't generally true, still it works well. So if it works well, we're going to use it. So Google has used the algorithm to classify mail in its Gmail system as spam and not spam, and it's been very effective. Recall that naive Bayes looks like this. The evidence is denoted by E, but we have also used the vector X in our class discussion. So instead of using E, we're using X. The evidence, or X, will generally not be a single simple event like windy equals true, but rather a compound event made up of simple events. So X is not just windy equals true, it's more like what we saw up here where we had the commas and we had this one, for example, here. So it wasn't just windy equals true, but it was outlook equals sunny and humidity equals normal and windy equals true and temp. So that's what the evidence usually looks like. Thus, on the right-hand side of Bayes' theorem, we may see something like this. On the right-hand side, so when we had that and here, but now it comes here. So it appears to the right of the vertical bar. So it appears there. So it might look like that. Recall that we have seen a form of conditional independence that looks like this. The probability, so we did study conditional independence, and this is what we came up with. You can look it up in the slides, you can look it up in Wikipedia. This is what we came up with. This means conditionally independent. Conditionally independent, the condition is Y. So it's, now this looks a lot like, regular independence would not have the Y here, it would not have the Y here, and it would not have the Y here. And that without those y's, this is a rule which, when satisfied, means that R and B are independent if you don't have the y's there. Now with the y's, we say that R and B are conditionally independent. This is a lot to go through in this video, but we did go through it in class. So I'm not going to go through it in as much detail right now. Okay, so recall that we have seen a form of conditional independence that looks like this, but this can easily be generalized to more events than just R and B. So it could look like this. So instead of just RB, you could have RBG given Y, and it would look like this. This would be called conditional independence for RB and G. So assuming now, going back to our particular problem, assuming that these events are conditional, the independence of these events, outlooks equals sunny, this, given play equals yes, use conditional independence to re-express this. So, but what does it turn out to be? Well, if we assume that these are conditionally independent of yes, then we're just going to get probability, outlook. So we're going to get equals, and then we're going to have the probability that outlook equals sunny, given yes, times, and then we're going to get the next one, which is, and times the next one, and so on. So it looks like this, except there's 4 of them instead of 3, because there's 4. 1, 2, 3, 4 of these. So there's 4 of these, but it looks like this. R, B, G given yes. If it's conditionally independent, it means that we can rewrite it like this. Again, we went through this in class. So it means that we can write probability of R given Y times the probability of B given Y, G given Y. So it's outlook equals sunny given yes, humidity equals normal given yes, windy equals true given yes, temperature equals high given yes. So what did they ask us to do? Use conditional independence to re-express this. So you would write it, this equals this string here. I'm not going to finish the last 2. Okay, let's take a look at question 41. So let's skip this right now and just look at this. So here we're talking about the probability of H given X. We could call it, again, the hypothesis given the evidence, or we could call it the class given the evidence, the class given the input. Anyway, we're trying to do this. Now, Bayes' theorem, we said, allows us to switch these. So let's use Bayes' theorem now. Bayes' theorem is true, always. So we're allowed to do this. We're allowed to write this. Now, this side we're not allowed to do unless we know that everything is conditionally independent. Okay, so this is, when we go from here to here, this is always true. But when we go from here to here, this is true if we assume conditional independence. And we said that our machine learning algorithm will make that assumption, even though there's no good reason to make it, but it does seem to produce a good classifier. Anyway, we're trying to learn how this algorithm is constructed. So we will assume conditional independence. Now, why is this a form of conditional independence? I mean, it doesn't look, up here, we said conditional independence looks like this. R, B, G given Y. I don't see that here. I just see X given H, not many things given H, just X given H. So it doesn't look like this has anything to do with conditional independence. Again, this is what conditional independence is talking about, the case where you have one thing, comma, another thing, given Y, and then it gives us an answer for that. But I don't even see that here. I don't see anything like that. I just see X given, maybe this is given Y, but the X is supposed to have 3 pieces there with commas, and it doesn't. It's just X. But X is a vector, as we call it a vector, and, X is the evidence, and we said the evidence is going to be something like this. We just call it X, this whole thing, but this X just stands for this. So this is an R, a B, and a G. Here's the R, a B, a G, and there's actually one more here. So there's actually not just 3 events here, there's actually 4. So if we call the first one this one, instead of calling it R, we'll just call it X1. And instead of calling the second one B, we'll just call it X2. And this is X3, and this is X4. So in that case, this X is really X1, X2, X3, X4, just like this is R, B, G, and then we can split the R's up like this. I'm sorry, the R, B, and G like this, so we can split the X1, X2, X3, in fact, all the way up to, we can just extend it to just be more general, up to Xn. So now let's think about what's written here. The probability of H given X, this part is always true. This is just Bayes' theorem. That's always true. We can prove it. It's not hard to prove. The next part is not always true. It's based on the assumption of conditional independence. If you make that assumption, then we can rewrite this piece here as this piece here. Let me make that in color if I can. So let's say this orange part there is this part here. Can't quite do that. Okay, so that is equal to that, and then P of H is still there, and P of X is still there. So this comes from the assumption of of conditional independence. Okay. So what does it ask us to do? Calculate the probability of yes, doing it this way. And that is, so you're supposed to do this to calculate this. Now, again, you don't need to do this for this data. This data, if you want to know the probability of yes given these, you just have to figure out which, let's just say what you have to do. So if you want to figure out outlook equals sunny, where's that? So let's put them in green, because we want windy equals true. Okay, let's put the other ones in green also. So I'll put outlook equals sunny, 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 sunny. Okay, and then we also want humidity equals normal. Let's get those. We don't have this. This is the wrong data. Okay, so anyway, we could do that. Humidity equals normal. We have to have different data here, not numeric data, but we could identify those, and we could get all the green ones, all the ones that we're interested in, and we wouldn't need, so we're trying to calculate, given those green ones, given that it's sunny and humidity is normal and true and high, so there's only going to be a very small set of those because they have to be green all the way across. So like, this one already wouldn't be included because this is green, but this isn't green. And this one wouldn't be included because this is green, but this isn't green. So the only one that's possible at this point, we haven't worked with these two variables yet, so we don't know whether these are going to be really possible or not. But the only ones that seem to be possible at this point is this row and this row, and then maybe those are not even possible. Anyway, once we have that set, then what's the probability of getting yes? So you could do it that way. But this says do it the other way, do it this way. So use the naive assumption and do it this way. Now, if you do it this way, that is the way I just suggested here, you're going to get one answer. You're going to get whatever you would get for this calculation. Now when you do it this way, you probably won't get the same answer, because this is based on an assumption which probably isn't true. So this is what our algorithm will give us, not this. This is really what we really want, but we're assuming this naive assumption, and that allows us to do, because we're assuming that, we're allowed to do this calculation, which we've discussed we discussed why we would want to do this. We discussed that in class. Okay, number 42. Okay, sorry. This question 41 wants us to do it the way I suggested here, by getting all the green parts and then figuring out the probability of yes. So this question wants you to do it that way. Now this question wants you to do it by calculating this. Okay, don't be surprised if your answer is not the same as the calculation in the previous question. Can you explain why the answer in the previous two questions may not be equal? Thus, we really should not have two equal signs in the above expression. Which equal sign is not justified? Okay, so this is not justified unless we say, assuming, like if we wrote up here a little note, assuming conditional independence, then it's justified. But without that, it's not justified. So can you explain why they're not the same? Because this makes the naive assumption, and this is just the original calculation. It doesn't have any assumption in it at all. But, well, just to explain, in class we said that this kind of calculation, when you have a lot of variables in X, in the evidence, in the input, when you have a lot of variables, you're never going to find even one case of something that matches all of these specifications. Like we have to find it, and probably even here we might not find it. So we have to find a case where outlook is sunny and humidity is normal and windy is true and temperature is high. Probably there are no cases of that in here. So you're just going to get 0. It's going to be problematic. But these, you will find cases of these. Like this says, yes, so the first one, yes, a given yes, the probability of, for example, outlook equals sunny. So can we find a case where we have yes and outlook equals sunny? Yeah, here's a case of that right here. In fact, there's two cases of that, here and here. So we can find cases of that, but we most probably won't find cases of these calculations. So that's why we need to make this assumption, this naive assumption, which is conditional independence. Okay? Okay, number 44, the right side of the expression with two equal signs above is called the naive Bayes estimate. So this part here is called the naive Bayes estimate of the particular class that we're trying to check about. So to determine which is the predicted class, we would check the naive Bayes estimate for each possible value of the class variable. In the weather nominal data, the class is play, and the two possible values are yes and no. So we would check this for yes, and we would check this for no. Suppose that we had a new example, a new day, but we did not know whether the people would play or not, and we wanted to see what the naive Bayes classifier would predict as to whether people would play or not. Suppose that the conditions, the X here, the evidence, is the following. Outlook equals sunny today. Temperature is cool, the humidity is high, and windy is true. Okay, what would be the naive Bayes estimate for play equals yes? So we need to open up the proper data set here. So not with the numeric values here, but rather with, I guess, temperature, whatever the temperature values are. I've opened up weather nominal. I'm going to save it on the desktop and then open up in Excel, and I'll try to use some of the same coloring scheme. We need to find out these here. So we're talking about outlook is sunny, temperature is cool, humidity is high, and windy is true. So we need to figure out each one of those. That is, we need to figure out our class that we're testing is play equals yes. So we need to figure out, given that play is yes, what is the probability of x1, which means this is our first one. So what is the probability that Outlook is sunny? So let's try that. So we're given that play is yes, so we have only to work with these rows. So we're only working with these rows. And now we're going to start with this one, Outlook equals sunny. And we want to figure out, given that H, that is, given that the class is yes, what is the probability that Outlook is sunny? So within the blue, we only have two cases where the Outlook is sunny. So the total number of blue is 1, 2, 3, 4, 5, 6, 7, 8, 9. So out of those 9, there are 2 that are sunny, so that's 2/9 is that probability. So the first factor here is 2/9. The next one we have to do is here. So that's when temperature is cool. So given the 9 that we have in blue, how many of them have temperature equals cool? I think it's just these. So that would be 3 out of 9. Okay, and we can color code them like this. Then we have to do the next one, which is humidity equals high. Okay, and I think there's 3 here. So that's 3/9 here. And then finally we have to do windy equals true. And windy equals true is, there are 3. Again, it's 3/9. Okay, so now we've figured out all these probabilities here in orange. Then we have to do times the probability of H. H is the probability of the class, or the probability of yes. So I think we figured that out before. That was, well, there's 9 here. So that's 9 out of 14. So that would go, I'll just put that here. Then we would need the probability of X. This is the prior probability of the evidence, of the inputs. Now here we run into the problem that we mentioned before. That is, we have to find at least one case where Outlook is sunny, temperature is cool, humidity is high, and windy is true. Now this is a subtle point, the way we're going to deal with this. Okay, but first let's just see if there is. Now we said that the problem with not just doing it this way, so that we have to go to this kind of formula and make this naive Bayes assumption, or this naive assumption, is when you have many conditions in here, it's going to be very hard to find even one instance that satisfies those conditions. So it may be very hard to satisfy, even to find one instance of this. So we have to make one last point here, but let's first check it and see if we can even find one. So what we need to do is find a row that has yellow, green, orange, and purple, and clearly there are none. So what that means is that the probability of this is 0. Obviously that's not such a great answer for this formula. So if you said this is 0, and therefore we get infinity here, that would be a reasonable answer, because we haven't discussed what to do in this case. But you can see that that's not going to really work too well, because, okay, so we just found out that probability, given the evidence of yes, is infinite. Okay, then we have to do the same thing for no. So what's the probability of no, given the evidence? We're also going to get infinity there, because the denominator is going to be the same, because the evidence, whether we're checking H is yes or H is no, this is the evidence that's going to be the same. We have a certain person, they are, or we have a certain day in this case, they are sunny, it's sunny, cool, high, and it's windy. And then we're just trying to predict whether people are going to play or not play. So this part is changing, but this part won't be changing in this prediction process. So this poses a big problem. So the way this is handled usually is just to ignore the denominator. Now you'll say, wait a second, what do you mean ignore the denominator? That's going to completely change the probability. That's going to change our estimate of what this is. If we take this out, just ignore it, and we just calculate the numerator, then the probability is not going to be correct anymore. we're not really concerned with whether it's correct or not. It's not even correct because of the fact that we made the assumption of independence, so it's not correct anymore anyway. We just want a way to say which one is higher, yes or no, that they're going to play or they're not going to play. So if we take this out, then we will get a value for the top for when it's yes, when the hypothesis is yes, when the class is yes. We can do this calculation. In fact, we just have to multiply these numbers times this one, and that will be the answer. And then we can do it for no, and we'll get a different set of numbers here because we won't be working with the blue here. We'll be working with these. We could make a color for the nose, but anyway, we won't be working with the blue set. We'll be working with the complement of the blue set. So we'll get different calculations here. So when we multiply this times this, we'll get an estimate of this. We don't even do this. Then when we do with no, we'll get a different set of numbers here. We'll get another estimate, and we can just choose the one which is higher. And that's actually the way the naive Bayes algorithm actually works. So what you would do is you would ignore the denominator, calculate the numerator for the yes value of h, calculate the numerator for the no value of h, and then just choose the one that's higher. That's the way the naive Bayes classifier would work. Okay, let's go to the challenge question here, number 45. So in this video, he uses the word likelihood around minute 6:30 instead of probability. Then he says we can convert them to probabilities. In the previous question, did we calculate what he would call a likelihood or a probability? So the term likelihood, and I'm not quite sure where the name comes from, why they call it the likelihood, but it is an important concept in probability. And this is a probability. We would call it a conditional probability, and we also call it a posterior probability. And when we switch like this, we call it the likelihood. So in actuality, we're calculating likelihoods here, probability, or something like this, a likelihood probability. Here's another perspective on likelihood. If we're considering something like this, then notice the O comes first and then the theta. That's equal to what we call the likelihood of theta given O. So for our purposes, though, we're just going to say that the likelihood is just the reverse when you reverse these. So instead of having the O here, you'd have it here, and instead of having the theta here, you'd have it here. Okay, the last question is, just before question number 40, we wrote, thus you may rightly conclude that there is no reason to use Bayes' theorem here, but we are working towards developing the machine learning algorithm called the naive Bayes algorithm. In that algorithm, Bayes' theorem will be advantageous. Can you explain why Bayes' theorem was important here? That is, why was it important to switch from here to here? So we started out with this, but we decided to use Bayes' theorem. But we said earlier that there didn't seem to be any particular reason to use it. So the reason is so that we can use the concept of conditional independence. Remember that this X is made up of actually many statements, and then we can split it like this. Remember that we had this. So we started out with something which was made of many statements, and conditional independence allows us to split it like this. So we want to switch from this to this because we want to be able to use conditional independence to get to here. And why do we want to get to here? Because we said that this is asking for the probability of H given this, but we're never going to find this. We said when we have many variables, so we won't be able to do it this way. And we won't be able to stop here, like we could go from here to here. We still won't be able to do it this way, because still we have to find an instance of X, and we won't be able to find an instance of X, because when X represents many variables, that means we have to find an instance that has outlook equals sunny, and this, and this, and this, and we have many conditions. We're not going to be able to find that. So we have to go from here to here, and still that's not good enough, but now Since we have something in this format, we can use conditional independence to get to here. And these are all possible to find instances of this, instances of this, instances of this, and so on. Now, if we hadn't made this switch from here to here, so that x was on the left side and h is on the right, then we would have h on the left side and x on the right, and that is not a form that conditional probability supports. In other words, conditional probability has to have the compound statement, which is here, has to be on the left side. There's nothing about conditional probability when the compound statement is on the right side. So the conditional probability works when we take a compound statement on the left side, and then we can split it like this. So, but if we hadn't switched the order, then the compound statement is on the right side. There's no conditional probability theorem that we can use here. So in order to be able to use the conditional probability theorem that we have to first use Bayes' theorem to get the compound statement on the left side of the vertical bar. So that's the answer to this one. Okay, that's the end of the answers to the Weka 4 set of videos.